All right, so we're going to do our third lecture on lines and planes. We've spent some time uh, last week looking at dot products, cross products, and various things that you can do with vectors and scalars and things like that. And today we're going to spend some time actually looking at what you do with these things. So this lecture is going to be broken up into three different pieces. The first piece is going to be about lines, and looking at lines in three-dimensional space. The second part is going to be about planes in three-dimensional space. And the third part is going to be about looking at distances between them. Usually this is sort of like a three-part lecture that we do during the year, so we're going to break it up to make it a little bit easier to navigate for people watching the recordings later on. Okay, so we'll get started. So suppose that you've got a point that's sitting inside of space. I'm going to call the point P naught is x naught, y naught, z naught, sitting on a line L in R3. And what can tell us about the entire line? So the image that we should have in our mind is, here's our line. And here's a point. We're calling this is going to be P naught, x naught, y naught, z naught. And it's going in, it's sitting on this line. So what else do we need to tell us about the entire line? Well, one thing that we can use is just that's a terribly drawn vector. One thing that we can use is just a vector that's parallel to the line. We're going to call this V. V is what we call a direction vector, A, B, C. So one thing we can do is we can find a vector that is parallel to the line. And as soon as we have a vector that's going in the same direction as the line, and a point on the line, we basically have the line itself. We have pretty much everything that we really need. So if you've got another point on the line, then a vector A, which I'm going to call P naught, that means it's a vector going from P naught to P. Actually, I should have that the other way around. That's a typo. If you go from P naught to P, we're going to call that vector A. That vector is going in the same direction as this vector V. This vector V down here is the same V that we had before. That's a vector that's going in the same direction as the line. So here's a question, and the question is, if you have that R naught is the position vector for x naught, y naught, z naught, and R is the position vector for x, y, z, then what's the relationship between R, R naught, and A? What's the relationship between these three vectors? Now, if we unpack that a little bit, and if we decide to, oh, come on, I'm getting random highlights here. Here we go. So if we decide to just expand this a little bit, what do we have? Here's R naught, right? Here's the vector R naught, and here's the vector R. I'm basically just redoing what this image is on the side, expanding it a little bit, and trying to make it a little bit clearer with less distractions. And then here's the vector A. And what's the connection between these three things? Well, the connection, it turns out, if you stare at that for a little bit, you'll notice that what we have here is that R, this is just simple tip-to-tail geometric interpretation of adding vectors, we see that R is actually R naught plus A times T. Putting this another way, this also gives us, so we've got R and R naught and A. Putting this another way, we also get that A, keeping in mind here that A is parallel to the vector V. So what that's really telling us here is that, so A is TV because they're parallel. So there's some scalar T, so that A is equal to T times V. This gives us what's called the vector equation for the line that's going through this point and with this direction vector. R is R naught plus T times V. Now, if we unpack that and expand that a little bit, just looking at the whole coordinate representation, this is R, and that's going to be x, y, z. And that's going to be R naught, we know is x naught, y naught, z naught, plus T times A, B, C. Putting that another way, with that also, to write that a little bit differently, x, y, z can be written as x naught plus at, y naught plus bt, z naught plus ct. In coordinates, if we break up all those coordinates, we get what are called the parametric equations. X is x naught plus at, y is y naught plus bt, z is z naught plus ct. Those are what are called parametric equations for this line through that point and along this direction. So what is this really telling us? What this is telling us is that you've got a point x, y, z on this line precisely when there's some real number t that satisfies all three of these equations. X equals x naught plus at, y equals y naught plus bt, z equals c naught plus ct. Of course, it has to be the same t in all three cases. Okay, so now suppose that we've got a, b, and c are not 0. Then we can isolate t from these parametric equations and arrive at what are called symmetric equations. What does that mean? Well, remember for a second that x is x naught plus at. I'm just rewriting the parametric equations right now. Y is y naught plus bt. Z is z naught plus ct. And we have, if you just subtract off x naught divided by a, what do you get? X minus x naught over a, that's t. Also, y minus y naught over b, that is also t. And z minus z naught over c, that is also t. So all three of these things are equal. So you can write this using what are called symmetric equations as x minus x naught over a equals y minus y naught over b equals z minus z naught over c. And altogether, these are what are known as symmetric equations. If you want, you can think about these, well, you should think about it this way, but if you want, you can write equals t at the end there. You don't gain or lose anything by doing this. It's just keeping in mind that, yes, this is in fact what this thing is equal to. What does this actually mean? This is telling us that you've got a point at x, y, z on this line precisely when these numbers satisfy these symmetric equations. Okay, so moving right along. Now, what if some of the numbers in the direction vector are actually equal to 0? Now, just remembering what the usual symmetric equations are, x minus x naught over a is y minus y naught over b is z minus z naught over c. The problem, of course, is what happens if a is equal to 0. And if that happens, then that's not good. You're dividing by 0 in that case, and bad stuff is going to happen. So we don't allow that. So what are we going to do instead? Well, remember where these come from. The parametric equations that we have just basically give us x minus x naught over a, right? So, or the parametric equations, rather, are x is equal to x naught. Now, ordinarily, I would say plus at, but a is 0 in this case. So we're actually not going to worry about that. We're going to ignore that completely. So I'm just going to erase that for simplicity. Y equals y naught plus bt. That's still the case if b is not 0. Z equals z naught plus ct. For symmetric equations, what is this? This is x equals x naught, y minus y naught over b equals z minus z naught over c. So these are our new symmetric equations. These are our parametric equations. And what does this actually mean? This means that for any point x, y, z on this line, the x-coordinate is constant. The x-coordinate is always going to be the number x naught. So this is sort of a special case here where you've got that one of the coordinates is in fact always constant. Now, suppose you have that a line L is the line that's passing through this point, 5, 1, 3, and is parallel to the vector I plus 4j minus 2k. So find the equations, the vector, parametric, and symmetric equations for the line. Well, in this case, we have that x naught, y naught, z naught is the vector 5, 1, 3. That's the position vector in that case. V, meanwhile, our ABC, our direction vector, is just 1, 4, negative 2. You can write this either using IJK notation or using angular brackets. They're both fine. In vector form, what this comes out as is R. Some people like writing R of t. There's absolutely nothing wrong with that. In fact, very soon we're going to see that that's fairly common. 5, 1, 3 plus t times 1, 4, negative 2. That's the vector equation. For the parametric equations, we can write this as x is x naught plus t, y equal, oh, sorry, not x, I'm not writing what the actual number is. 5, x naught is 5 in this case, it's 5 plus t, y is 1 plus 4t, z is 3 minus 2t. These are our parametric equations. And finally, we have the symmetric equations. Symmetric equations in this case are going to be x minus 5, x minus x naught. Now, if you want, you can write this over 1. You don't have to do that because it's just 1. That's y minus 1 over 4. And that's equal to z minus 3 over negative 2. Or if you want to be a little more aesthetic about it, x minus 5 is equal to y minus 1 over 4 is equal to negative z minus 3 over 2. Those are the symmetric equations. Okay, so that's the basic gist. So let's find two other points on the line. So remember that the parametric equations were given by x equals 5 plus t, y equals 1 plus 4t, and z equals, and then z equals 3 minus 2z. Is what we said. With all that in mind, what does that give us? Well, we know in this case that every point on the line has some t value satisfying these equations. So in particular, what that tells us is that what if we take t equals 1? T equals 1 is going to give us x is 6, y would be 5, 1 plus 4, and z would be 1. Or you could take t equals negative 1, which in this case would be x equals 5 minus 1 is 4, 1 minus 4, so y is going to be negative 3. 3 minus negative 2, or 3 plus 2, so z was 5. So 2 other points, are 6, 5, 1, and 4, negative 3, 5. Here's what this looks like. We've got our line, and we started off with the point. We know that we have the point 5, 1, 3 is what we started with on this line, but meanwhile, we also have the points 6, 5, 1, and the point 4, -3, 5. They all live on this line. And in fact, they're equally spaced. Okay, so now are they the only equations that define this line? No, they're not. We saw that the point 6, 5, 1, that's also going to be on the line. So another set of parametric equations is going to be given by, or could be given by, x equals 6 plus t, y equals 5 plus 4t, and z equals 1 minus 2t. Still using the same vector, the same direction vector, but a different point. There's nothing wrong with that. That's another way of describing, this line. All right, so suppose we want to find parametric and symmetric equations of this line that's passing through these 2 points. A is 2, 4, -3, and B is 3, -1, 1. Well, remember that we've got a formula for parametric equations and a formula for symmetric equations. Both of these formulas are given in terms of x0, y0, z0, which is a point on the line, and ABC, which is a direction vector that the line is going along. So we need those 2 pieces of information. We're going to need a point on the line, and we're going to need a direction vector that's parallel to the line. Well, one of these is very easy. The point we already have. We can basically choose either of these 2 points for this line because they're both going through. So 2, 4, -3, for example. That's a point that's on the line, so we're good there. We're set on that front. Now we can also take v equals AB to be the displacement vector from A is 2, 4, 3 to B is 3, -1, 1. What am I talking about? Well, again, we've got our line, right? And we've got 2 points that are on the line. So here's one point, here's A, and here's another point that's B. What we really need is a vector that's pointing in the same direction as this line. So why don't you just take the vector going from A to B? That vector will do the trick. Let's give that vector a name. We can call that V, and that's the vector going from A to B. And to find that vector, all you're going to do is just subtract the coordinates. So 3 minus 2, so that's 1. -1 minus 4 is -5. 1 minus 3 is -2. And that's really about all that there is to it. Let me just double check something for a second. 3, 2, 4, -3. Aha! I see actually that I made a mistake here, which is that I put the I put the wrong coordinate in here. That's okay. That's okay. So this should actually be -3. Sorry, this should actually have been +3 out here. So that's fine. We'll keep going. So I'll fix that when I upload these slides. So in this case, what this gives us is so here's the direction vector. So the parametric equations are given by, in this case, x is 2 plus t, y is 4 minus 5t, and z is 3 minus 2t. Those are parametric equations. If you want symmetric equations, for example, You can do that by finding x minus 2 is equal to y minus 4 over negative 5, which is z minus 3 over negative 2. So you can do that with either parametric equations or symmetric equations. And again, these encode the exact same information in both cases. What if you want to know where this plane, where this line intersects the xy plane? Well, let's think about what that means for a second. Here's the xy plane in your coordinate axes. The xy plane is simply all the points that are on this horizontal plane that's sort of at the bottom, so to speak, of our coordinate system. In other words, these are all points where z is equal to 0. So the xy plane, in other words, what xy plane really means, xy plane means that z is equal to 0. Now our parametric equations for our line were x equals 2 plus t. Oh, sorry, wrote that wrong. 2 plus t. Y equals 4 minus 5t. And z equals 3 minus 2t, is what we said. So if z equals 0, then what we really need here is to use the fact that z equals 0 with what we know z has to be for our line. And in that case, what that means is we have that 3 minus, so what that really is telling us is that 3 minus 2t is equal to 0. Well, the only way that happens is if t is equal to 3 halves. Okay, so t is equal to 3 halves. And if t is equal to 3 halves, what does that really mean? That means that we plug everything in to, because what we really need is a point where this is intersecting, right? So we're going to have x is 2 plus 3 halves, or in other words, 4 plus 3, so it's 7 halves. Y is equal to 4 minus 15 halves, or 5t, or in other words, that's going to be 8 minus 15, so it's going to be negative 7 halves. And z is 0 because it's the xy plane. So the point of intersection is going to be 7 halves, negative 7 halves, 0. Okay. So let's keep going. Now, by the way, sometimes it's useful to have a way of parameterizing just a line segment. And doing that's actually quite simple. If you're working with a line segment, then all you really need to do is consider x naught, y naught, z naught for one point on the line segment. On the opposite point of the line segment, we'll call that x1, y1, z1. You still have to find a direction vector, and the direction vector is quite simple. It's just the vector of displacement from A to B. And that's going to be x1 minus x naught, y1 minus y naught, z1 minus z naught, exactly what we just did. And in that case, we can have r equals x naught, y naught, z naught, plus t times that displacement vector. I'm not going to read it aloud. You can read it right there. But if you do the algebra, if you actually do the algebra out, you'll find that's the same thing as saying r of t, thinking about this as a function of t now, r of t is 1 minus t times r naught plus t times r1, where r naught and r1 are the position vectors for our points A and B. It's a nifty little formula for the line segment because you'll notice that one of the things that it gives us is that r of 0 is r naught, and r of 1 is r1. It's a nice little trick that allows us to cleanly parameterize a line segment. All right, so the last example I want to look at here is with these two lines. So we've got L1 is 1 plus t, x is 1 plus t, y is negative 2 plus 3t, z is 4 minus t. L2, x is 2s, y is 3 plus s, z is negative 3 plus 4s. So the question is, are these lines parallel? Well, if they are parallel, then they have to have parallel direction vectors. So the direction vector for the first one, let's call that v1. v1, the direction vector for the first, is 1, 3, negative 1. The direction vector for the second is 2, 1, 4. By the way, notice that the parameter for L2 is s. The parameter for L1 is t. It's a little more standard to write the parameter as t, so why am I writing it as s for L2? The reason is because I don't want to imply that the parameter for L1 and L2 have to be the same number. And in a little bit, we're going to do a problem where we're actually going to say, no, they might not be the same number. They could be different numbers entirely. That's okay. You can allow that to happen. But in order to account for that, we're going to have them be different symbols. One's going to be t, the other's going to be s. Now, we've got the direction vector for the first one. For the first of these lines is 1, 3, -1, coming from the coefficients for t. And for the second line, it's going to be 2, 1, 4, the coefficients for L2. So what does that give us? What that's going to give us in this case is that, well, are those things parallel? No, they're not. They're not parallel because they're not scalar multiples. Parallel, I can spell. Now, if we were living in two-dimensional space, the fact that these lines are not parallel would mean that they would have to intersect. But the thing is, we're not living in two-dimensional space, we're living in three-dimensional space. So the story is a little bit different here. So do these lines intersect? Well, a point is going to be on XYZ. A point XYZ is on L1 precisely when there's a number t that satisfies the parametric equations for x, y, and z. And likewise for L2, for the parametric equations for L2. Now, they're only going to intersect if there's a point on both lines. In other words, you have to have the parametric equations for L1 and the parametric equations for L2 be satisfied for the same x, y, and z. It might not be the same t and s, but it will be the same x, y, and z. So you've got to have some t and some s so that both sets of parametric equations are the same, that they both agree with each other completely. So we're going to have to solve this system of equations. So here's the system. Now what this tells us, now the first of these equations tells us that t is equal to 2s minus 1. So we can substitute that into the second equation. So the second equation in that case gives us -2 plus 3 times 2s minus 1. Okay, we're just unpacking that. That's going to be -2 plus 6s minus 3, or 6s minus 5. But we're told that that's the same thing as 3 plus s. To put that another way, that means that 5s must be equal to 8. Well, that's only going to happen if s is equal to 8 over 5. So far, so good. That gives us a number for s. Now, we know that t is 2s minus 1. We found that from the first equation. In particular, that means that that's going to be 2 times 8/5 minus 1, or in other words, 16/5 minus 5/5, so in other words, 11/5. So we have, in other words, that t equals 11 over 5, and s equals 8 over 5. That's great. That's great. We have a number for t and a number for s, and if they intersect, then we know what t and s are. So we're done, right? No, we're not, because come on, can't get to the same slide. There we go. So we're not done. The numbers t equals 11/5 and s equals 8/5, they do satisfy the first and second equations, but it's not enough. They have to satisfy all three of them. And if we plug in those numbers into the third equation, which was 4 minus t, the third equation we can see here is 4 minus t equals -3 plus 4s. And if we do that, then what we end up getting is the nonsensical equation, 9/5 equals 17/5. Well, that's obviously not right. So these lines don't intersect. They're what are called skew lines. They don't intersect, but they're not parallel either. So that's what we're working with in this case. So that's so we'll stop there for now, and then we'll pick up the part 2 as the next video.